Welcome to the Process Simulator tutorial. In this session, we have two main objectives. First, we'd like to show you how to build a simple manufacturing process model on your own. And second, we want to demonstrate how you can use a simulation model to answer questions and to solve problems. Process Simulator works as a plug-in inside of Visio. That means that Visio must be installed first, and it has to have been opened at least once before you can install Process Simulator. Let's begin by looking at our completed model first. Here's a model of an electronics manufacturing process that uses printed circuit boards, or PCBs. Let's walk through the model. Right now, in its current state, about 20 PCBs are initiated each day. The first step is to clean and prep the PCBs. Then they move to a vacuum bake oven where they're batched in a quantity of 8. Then the PCBs are unbatched and installed. Then finally they're inspected and tested. If they pass the test, then some statistics are recorded and they exit the process model. If they don't pass the test, then they have to go through rework. Now you'll notice under each activity, I've added a few notes. For example, here we see that this process step takes around 12 minutes. We're going to use a uniform distribution with a mean of 12 and a half range of 2 minutes. That's the same as about 10, 12, or 14 minutes. Here, the batch operation will take 60 minutes every time. When we install the PCB, we'll use the same distribution that we used in Operation 10. Inspection and test, we'll use a normal distribution with a mean of 10 minutes and a standard deviation of 1. The rework step can vary anywhere from 10, 20, or 35 minutes, so we're using a triangular distribution here, using those numbers as the min, mode, and the max. And finally, in Operation 50, when we record the statistics, it takes about 2 minutes. Now you'll notice that each activity has a capacity of 1. And we have a couple of resources. Our line operator is utilized in Operation 10 and Operation 30, the two blue steps. Operation 20 and 40, these use automatic equipment, so no personnel are needed. The pass test activity is really just a decision point, so there'll be no additional time here and we will not need a resource. Finally, we can see that we have about a 20% rework rate. 80% of the time the products are good, 20% they have to go here. Now I'll hit the Simulate button and we'll watch the animation run and make a few comments. First, I'll zoom to fit the layout so that we can see it better. 20 PCBs arrived, and as they process through, the input buffer for Operation 20 gathers 7 and then 8 entities. When the 8th one shows up, then the batch enters the empty oven. Later they're unbatched and proceed through the other process steps. For the rework determination, the model will randomly decide 20% of the time which entities need to go over to Operation 45. The remaining 80% just proceeds straight on to Operation 50. As the model runs, we can see on screen a count of the exits, as well as the average cycle time for the entities that have already exited. We also notice that the resources change colors from time to time. As a resource is captured and utilized, it will turn green. When it's not being utilized, it will turn its normal color. If there's a downtime for the resource, it will even turn red. We also notice up in the right-hand corner the simulation clock. So far this model has run about 10 hours. Now it's set to run for a total of 48 hours. There's one 8-hour warm-up period, then another 40 hours. This will allow the model to fill up and warm up and then run a 40-hour typical week. You'll also notice that we're running the model 30 times. We run models more than once in order to allow the probability distribution expressions to randomly pick different values. This will give us a different look at the process each of the 30 times that we run it. As the model runs, I can adjust the animation speed by using the slider bar up above. I can even turn the animation off, and the model will run through all 30 of its replications very quickly. Would we like to view simulation results? We'll look at simulation results later. Right now, I'd like to demonstrate how to build this model. First, let's open Process Simulator using our desktop shortcut. You'll notice that Visio is actually opening, and Process Simulator is one of the menu ribbons inside of Visio. We'll close the Getting Started window and look at our layout screen. You'll also notice to the left, since we're using Process Simulator, Visio has opened the Process Simulator stencil, so we're ready to begin building our model. Now there are a number of ways to add shapes here. We can use the Auto Connect feature like this, hover over one of the little blue triangles, and just keep adding shapes. So I'll use Auto Connect and build most of our model. Now we don't have an entity yet. That's the thing that moves through the model. So we'll go back over to our stencil and I'll pick the disk entity icon. We'll add it right here. Since it did not automatically connect to the first activity, I need to go into Visio, into its home ribbon, and activate the connector tool. Now I can hover over the disk entity and drag into the first activity box. I'll also drag a connection from activity 6 to activity 7 and then let go of my mouse. Then I'll drag from the center of activity 7 a connector over to the right. This will make an exit routing. Now that I've made all my connections, I can make an adjustment or two if I need to. I'll select the pointer tool and I'll drag this connection over here so that we can plainly see it. I'll also just zoom in right now. So there's a couple of ways to do that. I can view fit to window, or I can hit zoom and select one of the magnifications, or I can just simply hold down the control key and use my wheel on my mouse to get the right image and the right size that I want. Now that we have our main process steps, we can change the activity names to match our process flow. In Visio, you can simply select an object and then begin typing. There's operation 10. Next I'll do operation 20. Activity 4 then will become operation 40. Activity 5 is just simply pass test with a question mark. Activity 6 is operation 45, rework. And finally, activity 7 becomes operation 50, record the unit statistics. Next, I'll change our disk icon so that it's now called PCB. I'll also go over to the right and adjust the percentages coming out of past tests. Now there's a couple of ways to do this. We can just click right on the number here for what's called a percentage routing and change the percentage right here. Now watch as I change 1, it no longer adds up to 100%, so it looks like we have an error. But I can go right over here and adjust the 50 to an 80, then the red error goes away. Next I'll come back to my stencil and I'll select a couple of icons for my resources. For my line operator, I'll use this assembly tech icon. And for my inspector, I'll use this worker icon. And again, I can simply click on the icon and change the name. When you build a model in-process simulator, it uses some default data in each of the model elements. However, now it's time to change the default data, and we'll do that by looking at properties. First, we'll start with this arrow with the hollow arrowhead. This is called an arrival, and it has properties right now that will allow periodically a quantity of one PCB entity to arrive every 5 minutes. We want to adjust this a little bit. We want our PCBs to arrive every 8 hours, all in one group. In our current state, we're trying to work on 20 PCBs each day. The 5-minute start time really only applies to the very first arrival of the first PCBs. So we'll use these settings for our periodic arrivals. Let's continue across and adjust the properties for the other model elements. For operation 10, you'll notice that by default there's a triangular expression of t, 3, 5, or 10 minutes. We want to change that to a uniform distribution, so I could just type in U parentheses 12, comma 2 parentheses. Another way to create an expression like this is to right-click in this field and open the distribution builder. This would also allow you to select a number of distribution expressions and enter their parameters right here. Then when you hit OK, it would paste the expression in the field. We'll leave our capacity of 1 and we'll leave our input buffer at 999. This allows some entities to come in and wait their turn until there's available capacity. Also in this step, we want to use the line operator for this amount of time, so we're going to select that here. You'll notice that there are a number of other features down below. You can adjust availability and set batching and other parameters for the activity if needed. Let's go to the routing from operation 10 to operation 20. Right now it has a default move time of 1 minute. We'll change that to 10 seconds and we'll use the line operator to carry that part from operation 10 to operation 20. In operation 20, we'll leave our capacity at 1 and we'll leave our buffers at 999. However, our time for this step is going to be an even 60 minutes because we're using the oven to bake a batch of PCBs. So down below, we want to use the batching feature. Before the activity begins, we want it to batch 8 PCBs, and it will use the input buffer to gather those batches until you hit the target number of 8, and then it will allow them to enter the oven, which has a capacity of 1 batch. Next, we'll go to the routing between operation 20 and 30. Again, we'll change this to 10-second move time, and we'll use the line operator again. In operation 30, we want to unbatch before we begin anything with the PCBs. Our time for operation 30 will be the same uniform distribution expression we used before. So this time, I'll use the distribution builder. I'll go down to Uniform, and I'll select 12 and 2 for the half range, and hit OK. We'll leave the capacity at 1, and we'll leave the input buffer at 999. This operation also uses the line operator, so we'll select them here as well. Now the routing coming out of operation 30 and operation 40 does not require a person, however the time needs to be adjusted again. We'll change the move time to 10 seconds, but we will not use any resource. In operation 40, we'll leave the capacity at 1 and the input buffer at 999, but we'll change the distribution expression to a normal distribution with a mean of 10 and a standard deviation of 1. Operation 40 is an automated task, so it does not use any resource. Coming out of operation 40, the routing that goes to pass tests will take about 10 seconds for the move. And in this move, we'll use the inspector. Pass test, like most decision blocks, will not take up any more time, and it's set at an infinite capacity, and no resources are needed. This is really just simply a point to send entities the proper path. The 20% is already set. However, we don't want to move time here, so we'll zero that out. And the 80% is already set. We'll change that move time also to a 0. In operation 45, again the capacity is 1, but we want to change the time. It is a triangular distribution expression, but we'll change it to 10, 20, and 35 minutes. And in this operation, we'll use the inspector. The routing from operation 45 to operation 50, again will have a 10-second move time, and for this move, we'll use the inspector. At operation 50, again our capacity is 1, and our input buffer is 999, but our time will be an even 2 minutes. And again, we'll use the inspector for this step. Now the last routing, the exit routing, we'll set that at 0 time, because you really don't want to add any more time to an entity once processing is complete. Now let's look at our resources. The line operator, the properties show it has 1 unit. Now we could change this to 2, 3, 4, or any number and display them all graphically. But for our purposes right now, the current state of this process only uses 1 line operator, so I'll change this back to a 1. And as soon as I click out of that box, that other icon goes away. The inspector also has just 1 unit, and we're displaying him graphically as well. Notice that for resources, there are additional fields in the properties. You can add cost, you can even adjust the availability, and you can even add shift files or calendar files here. Now we can add a few other embellishments to the model at this point if we want to, but it's really ready to run now. So let me just add some text and a couple of other things. We'll call this our electronics manufacturing process. I can also change some colors of a couple of icons if that helps me associate some things that are going on. For example, here the line operator is blue and these couple of boxes here are blue, so that for the 2 that are automated, I'll just change their color to gray, something else. And I'll color code also the steps where we're using the inspector. I'll change his color here to orange, and likewise the two boxes where he's performing. I could add additional notes above or below each activity with process times and other information, but I'll leave that off for now. Let me save the model. I'll just put it on my desktop. And next, I can adjust the simulation options. In simulation options, this is where we set the run length and we indicate whether we want a warm-up or not. I'll set the warm-up at 8 hours, followed by a 40-hour time-only run. Under the Animation tab, the default is to enable the animation, but we could select it and turn the animation off, and the model would run a lot faster. We'll leave it on for now. One other adjustment in the Run Length tab, I will change the replications from 1 to 30. We never want to run a model just one time to make decisions. We want to run it multiple times and take advantage of the random variation that's generated from the probability distributions. I'll hit OK, I'll save the model one more time, and now it's ready to run. So now I'll hit the green Simulate button, and we'll watch the model begin to run through its 30 replications. I'll zoom to fit, and I'll let the model speed up a little bit, but I'll go ahead and hit the animation button so that it quickly finishes its 30 replications. And this time we will view the simulation results. Now the story with this process, again, is that each day they're initiating 20 PCBs. That would be a target of 100 per week to get completed. But as we can see from our results, their total exits for a typical week is only 94.13. And here we see the average time in system in minutes. If I want to convert that to hours, I'll go down to options in the left-hand corner and just select hours. So it's taking, on average, about 8 hours to get a PCB through the process. Now let's look at the other 4 charts that are generated every time we run the model. Up in the top left-hand corner, here are the entity states. And if I right-click on this chart, I can add data labels. So what I see right now is that about 5% of the time a PCB is in movement. 20% of the time it's waiting. That could be waiting for a resource or waiting to be part of the batch. 21% of the time it's in actual operation. And then 53% of the time it's blocked. Blocked means that it's done where it is and it would like to move on, but there's no available capacity ahead. To the right, I can see the resource states. Again, I can right-click and just add data labels here. So now I see that the line operator is utilized about 97% of the time, and the inspector about 25%. If I look in the bottom left-hand corner, I see the single capacity activity states. Again, I'll right-click and add some data labels, and I'll also go down to the bottom left options, and I'll sort these by the percent in operation. And now the activity with the highest utilization is at the top of the chart. Operation 10, clean and prep. It's in use 49% of the time, and 22, almost 23% of the time, the entities there are waiting. If I look at the multiple capacity activity states chart, again, I can right-click and add some data labels. And for this one, I'll go down in the bottom left corner, options, and I'll sort it by percent partially occupied. And at the top of our chart, Operation 10, clean and prep input buffer, is listed. So the multiple capacity activity states for this model are all of the buffers as well as the pass test decision block, which has an infinite capacity. There are a number of options available in the output viewer. For example, while we're looking at this chart on the multiple capacity activity states, if I did not want to see all of those activities listed, I could just deselect them from the items list on the left. I can also, for any chart that looks like a table, I can adjust the columns. And we'll see in this case, there's a little bit more data over to the right. Average time in operation is right next to average time in system. So again, these 5 charts are all generated every time your model runs. They repopulate with the latest data. But you can also build additional charts. So now I'll add just a few more. This is the entity count chart. I'm going to adjust it a little bit. Instead of looking at entity exits on the hour, I'm going to say let's look at them every 8 hours, and I'll change the x-axis to hours. And like the other charts, I can right click on this and add some data labels. The numbers are a little small, so I'll go under Format, and I can make a few adjustments here. Get rid of some zeros, go to Data Labels, make the numbers a little bit bigger, and even get rid of some of the extra zeros here if I want. So what this chart is showing me is for each of the 5 8-hour days, here's how many PCBs exited. Now this is after the warm-up period has occurred. So this is in effect a breakdown of those 94 exits. Now we can add some other charts to this as well. I'll go up here to Column Charts and add a variable summary chart. I'm going to left click on my mouse button and drop it here to the left of this chart. And it will automatically select all of my variables, but I really am only interested in the exits. I'll right click and add my data labels, and once again I'll make the data labels a little bit bigger, easier to read. So this is the 94 exits on the left side. Now on the right side, this is how many exits each 8-hour workday. I'll add just a couple of more charts. Under Charts, Tables, I'll go to Entity Summary. I'll left click and I'll drag it and place it below both of these other entity charts which we've made. So again, this is the table with some of the data for our PCB entities. 94 exits. There's currently 10.3 in the model when it stopped running. Here's my average time in system. Again, it's easy to convert that from minutes to hours. And then we have move time, waiting time, actual operation time, and blockage. Now the average time in operation is when we're adding value to the PCB entity. In this model, that would be the 1-hour bake time in the oven, and then the balance of this is the time that the entities are spending with the different resources. So we can see that on average, the processing time for one PCB is less than 2 hours, but it takes us nearly 8 hours to get through the system because of blockage and waiting and movement time. Now I'll add a couple of other charts that may be of interest. Let's look at the Activity Summary table. This shows a lot of data for every one of the activities in the model. And what's neat about the tables is you can sort the tables by clicking once or even twice on one of the column headers. So now I've sorted this entire table by its current contents. This shows me when the model stopped running, on average, how many entities were at each activity or location. Now again, all of these figures are decimals because this is the average of 30 replications. So on average, out of the 30 reps, we're seeing a little over 6 PCBs are in operation 20 input buffer, and a little over 1 is in the operation 10 input buffer, and then there's a couple of others scattered around in other steps. We can also see from this table the maximum contents right here at clean and prep input buffer was 20, a little more than 20. We know that when the model starts up and every 8 hours later, 20 PCBs are entering at the first location. They're arriving. So the maximum contents shows that sometimes there's more than 20 there. So let's make another additional chart. Let's do a time plot, and we'll select the operation 10, but we want the input buffer, which is down here. The input buffer is where all of the PCB entities are actually arriving to. And we'll change the view just a little bit. We'll go to Custom, and we'll look at the contents in that buffer every 5 minutes. Now this is interesting. This shows us that on average, as the arrivals occur, we can see how they're finally working them off out of the input buffer. They're departing, going into operation 10 activity, and then operation 20, and so on. We can see how those arrivals are counting down. Most of the time, they get empty, the buffer gets empty before the end of that 8-hour day. But sometimes, it still has 1 or 2 left in the buffer. Then when another 20 arrive, it just increases the amount that are there. So we're not always completing all of the entities from that very first location. Let's make one more chart just to show you how easy it is. We can click on buttons up here to make a number of charts. I'll do an entity states pie chart. Now this is the same statistics and the same data that we saw on our initial scoreboard report over here. However, right now it's just shown as a pie chart, and you can actually, if you have more than one entity, have numerous pie charts in here. Each of these worksheet pages in the output viewer we refer to as a report page. Not only can you add charts, but you can also edit the titles to these. So we'll just call this one Activity Sum Table. You can also move these around, or if you create one that you don't need, you can just simply delete it. What's nice about all of these charts that we've created and formatted, all of these tables, is once we close the output viewer, as long as we save it before we shut it down, then all of these charts and tables will repopulate with new data the next time we run the model. However, if we don't save them when we close this out, then they'll all go away, and the only thing we'll have are the 5 default charts that we mentioned earlier. If you want to export any of these charts or any of the data, you can simply go up to the Export menu, and for a picture of the chart, just go to Export, Picture, Chart. That's the same as Control-C. And then when you go into, say, PowerPoint, you can do a Control-V and this chart will appear. If you want to export the data itself, let's say for a certain time series data element, we could go into here and have many options to select. If I wanted the cycle time for all of the entities that were coming through the final operation 50 step, then I could simply name the file, set the path, and export it to Excel. Then immediately I have the Excel file available, ready to open, and I can study all of that time data for each of the 30 replications. Now let's go back to the model. Up to this point, we've built a model of our current state, and it appears to be fairly valid since the data from the output viewer from the model appears to match very closely to what we're actually seeing in the real world. So what can we do with this model? Every time you build a model, you have to know up front what questions are we trying to answer, or what problem are we trying to solve. In this case, we're currently trying to manufacture 20 PCBs a day, and we're falling short of 100 per week. We're only making about, on average, 94. Management would like this process to manufacture 175 per week. So that's our target. That's why we built the model. Management wants to know, what will it take to make 175 PCBs from this process? So how do we begin? We can use the Scenario Manager tool to temporarily change some of the elements within the model. We know that 20 per day is 100, therefore if we're trying to make 175 per day, that would actually equal 35 coming into the model. So we can look under our periodic arrivals and change our quantity, add that parameter to our Scenario Manager tool. This is the current amount. We're trying to make 20 per day. We could simply add a scenario that says 35 a day, run it, and then see how the model responds. But first we'll have to change this 20 to a 35. We've already run the baseline. I don't need to run it again. So I'll just run this scenario. So let's be clear what's going to happen. The 20 per day that we had initially in our baseline model is actually still there, hard-coded into the arrival routing. But the Scenario Manager will allow us to temporarily change that number to a different value. So when I run just this scenario, it will feed the model 35 PCBs every 8 hours. And let's see how the model responds to that, and then we'll compare it to the baseline. Once again, we're going to run 30 replications. Up in the top left-hand corner, I can see that I'm running this scenario 35 a day. I'll go ahead and turn the animation off, and we'll get right to the output viewer. Now let's compare the baseline data to our scenario for 35 a day. It looks like we're only making a couple more per week. Let's look at the entity count report. So before we were averaging around 94 per week, and now we're only averaging 97 to 98 per week. We can see here the output for each 8-hour day. So there's not a whole lot of difference. So what's going on? Let's look at our time plot once again for the Operation 10 Clean and Prep Input Buffer. This is the arrival location for our PCBs. Before we noticed that the input buffer was emptying out most days or almost emptying it out. If we add the 35 a day scenario, watch what happens. The green line now at the bottom is our baseline data. The 35-day scenario data is the blue line. And notice that in this scenario, the buffer never empties out. It grows and grows. In fact, it ends up over here to the right when the model stops at about 85. If we look at our activity summary table and change so that we're looking at the 35 a day scenario data, we can see the current contents when the model ends, again, is right at that 85 number. And it's in that same location, Operation 10 Clean and Prep Input Buffer. So a lot of the PCB entities are getting stuck right near the beginning of the model. So what's going on? Let's look at our resource states. In the baseline model, the line operator was already at 97%. If we look at the 35-day scenario, now the line operator is at 100%. So what's happening exactly? We simply increased a flood of PCB entities from 20 to 35 into our model, but the line operator that works on them at the very beginning of the process was already at almost max utilization. So all we've done is bump his utilization up a little bit and get a couple more through each week. So turning on 35 a day is not going to solve the problem. That just creates more of an issue for our line operator. So let's go back to the model and come up with another scenario. Since the line operator utilization is so high, it appears that we're going to have to add more resources to this model if we want to get more PCBs through. So I'm going to go back to the Scenario Manager, Add Parameters. This time I'm going to go to Resource Units, Line Operator. Our baseline, we have one line operator. We want to add another scenario, 2 line ops, we'll call it, and we'll stay at the 35 a day for the arrivals, but we'll change one line operator to 2. Now let's run just this scenario. Again, this scenario will continue to have 35 PCBs arrive each 8-hour day, but there will be 2 line operators. Even though we don't see them here, there are 2 line operators since we're overriding the baseline value using the Scenario Manager tool. We can see here that we're running the 2 line operator scenario. So I'll turn the animation off and we'll go back to the output viewer. We'll look at our entity count first to see if we're getting more PCBs through the process. And we are. With 2 line operators, now we're averaging 175 per week. We're hitting our 35 PCBs per day target. So it's clear that the main thing that we need to do is add an additional resource to the beginning of our process. But let's look at some of the other charts we built to see how they look as well with this scenario. So in the time plot, if we check the box for the 2 line operators, then we notice that our buffer is emptying once again. If we look at our activity summary table, and let's look at just the 2 line operators scenario, the current contents is emptying out as well. We only have a handful of entities left in the process when it ends. Now let's look at our resource states. We'll add the data from the 2 line operator scenario, and now we can see that each of the 2 line operators are utilized about 88%. And if we look at the inspector's utilization has risen to about 47%. So the additional line operator is allowing us to increase our throughput of PCB boards and reach our target of 175 per week. However, the resource states and their high utilization causes some concern. When we started, we were almost at 100%. We rose to 100% with the 35-day scenario, and currently we're at 88% utilization for each of 2 line operators. However, in the real world, utilization for labor above 80% can be difficult to sustain. So we might even recommend that a 3rd line operator be added. We could certainly run additional scenarios for this model. We could experiment with what if we had 2 vacuum bake ovens. We could change our capacity to 2. We could also change our capacity to 2 for inspect and test and see if that made any difference. So there are a number of other scenarios that we could run. We could add a 3rd line operator. We could even increase our arrivals to maybe 40 per day to give us a little extra production volume at the end of the week. I'll add a few more parameters to the Scenario Manager just so you can see how to do these other types of scenarios. If you want to experiment with activity time, you want to just simply select some or all of the activity time parameters that are available. If you want to experiment with activity capacity, then again, just select the parameters on the list inside the folder for capacity. Now let's look at the Scenario Manager. We've mainly been working with the quantity of arrivals and our line operator units. But here are the parameters that I just added for all of those time elements for each process step. Again, these are the baseline default numbers. However, if we want to run additional scenarios, it will copy those baseline values over and allow us to edit them. If we want to change our capacity, in other words, if we want to simulate what would happen if we had 2 vacuum bake ovens, we could do it right here just by changing the 1 to a 2, or the inspection stations from a 1 to a 2. So it's easy to run scenarios in the Scenario Manager, and the big advantages are you have a data record in the output viewer which is individual to that scenario, and it does not corrupt or mess up your baseline model at all. We're not changing any of the default values. When we use the Scenario Manager, we're just temporarily changing them to derive new data from the model. Now I'd like to show you a few more features of the Process Simulator software. You may have noticed, as we looked at properties for activities, routings, and arrivals, that there was always a logic window next to the properties. In the logic window, you can use statements to write code to execute different operations at an activity, at an arrival, in a routing, or even a buffer. Back in the Process Simulator ribbon near the top, you'll notice some other model elements. Attributes can be created by the user to assign and hold values that represent characteristics of an entity. Variables are also user-defined expressions, but these are used most of the time to help track metrics that you create. Arrays are like spreadsheets full of data, which can be imported into a model or exported from a model. Macros are also user-defined expressions. These can hold numbers or probability distribution expressions. Subroutines are independent blocks of logic. You could put a subroutine within another block of logic, or you could have a subroutine run all on its own. Other model elements include resource groups, user distributions, external arrival files, or external files in general, initialization and termination logic. Also, under More Tools, we have ways to create model packages and install them. You can import or export data to and from Excel for your entire model, and there's also a StatFit application which allows you to fit your data to a distribution. There's also a link to Launch Minitab, and we have a Six Sigma feature that will export to Minitab. In addition, we have a calendar editor. This can be used to create calendar files for company holidays, vacations, or plant shutdowns. It can also be used to create shift files to put your workers on work shifts in the model. I hope this tutorial has helped you better understand how to use Process Simulator to build simulation models, as well as how to analyze the data and answer what-if questions about them. Process Simulator is a simple but robust tool that will allow you to build a model of a system, even changing individual element properties. This allows you to study process behavior, answer what-if questions, compare proposed changes to see if they would be effective, and even determine the optimum settings for a process. If you'd like more information about Process Simulator, feel free to contact us. Thanks for watching.